11 episodes ago, we first discussed the invention of the telegraph in the 1800s, humanity's first step towards being able to communicate over long distances. And looking back, the technology looks so basic. A long cable and a switch that turns on or off an electric signal that travels through that cable. We compare that to the phones and computers we have today, and it's easy to feel that our technology is far superior and so much more advanced. And look, undeniably it is. But amazingly, at the core of all our fancy phones, screens, and wireless communication is the exact same thing as the first telegraph. A signal that switches between on and off and travels along cables. That's it. All of this whole modern world runs on that, on or off. Only we call that system binary, and instead of on, we use the number 1, and instead of off, we use the number 0. And all of this amazing digital world can be boiled down into that, a staggeringly fast stream of ones and zeros. How does this process work? Well, let's find out. Computers, for much of their early history, were only used to compute incredibly large amounts of numbers. And it may not seem like it, but nothing has really changed today. Underneath the hood of all our touchscreens, 4K displays, games and YouTubes is just an incredibly complex and fast stream of numbers being processed. And the language that defines that stream of numbers is called binary. The binary numbering system was refined and brought into prominence in the 17th century by Gottfried Leibniz. It should come as no surprise that he also created one of the earliest ancestors of the computer, an arithmetic machine he called the step reckoner. So a simple explanation of binary is this. In maths and computers, the smallest unit of data is called a bit, or a binary digit, and that bit can have one of two values, either a 1 or a 0. This is why it is known as a base 2 system. Our standard decimal system we use in mathematics is a base 10 system, where each place in a number can be one of 10 different digits, from 0 to 9. So for a computer to operate at its most basic function, the processing of numbers, we need to find a way of converting base 10 numbers to base 2 numbers, or convert decimal values to binary values. So let's do that right now. Let's start with the number 232. If we break this number down, it is made up of 2 100s, 3 10s, and 2 1s. If we lay this out on a table, you'll see that as we work from right to left, each column is 10 times the value of the previous column, because we're working in base 10. So now let's consider a similar table, but this time in base 2. You'll notice the columns from right to left are multiplied by 2 each time. So if we input the binary number 101 into this table, we have 14, 0 2s, and 1 1, which when added up equals 5 in base 10. So 101 in binary is the number 5 in our everyday decimal system. Now let's take it a step further and convert our original number 232 into binary. First, let's lay out our base 2 table working with 8 bits. Now let's start from the left. Does 128 fit within 232? Yes, so let's mark a 1. So now let's add 128 to 64. Does that still fit within 232? Yes. So we mark another 1 in that column. Now we'll add 128, 64, and 32 together. Is it still less than 232? Yes, it still is. So now we'll add 128, 64, 32, and 16, which will give us a total greater than 232. So we mark a 0 in this column. The next column gives us our exact number, so we mark a 1. And now that we have our total, we then mark zeros in the remaining columns. Now we can see 232 in binary is 111010000. Quite a simple conversion when we lay it out like this. Now there is a lot more complexity to this as we get into decimals and negatives, but this should give you a basic idea of the process that connects these two numbering systems. So how do we deal with the alphabet in binary? Well, each letter and symbol is assigned a number, and that number is converted into binary just like we did then. So the capital letter A is assigned the decimal value of 65, which converted to binary is 01000001. So say we wanted to write the word process in binary, it would look like this. Now how about images? How does your grandma's blurred selfie where she's barely in frame get converted into a signal that can be sent from her phone to yours? Well, firstly, that image is broken down into individual dots called pixels, and each of those individual pixels has a color. Colors on a computer are broken up into varying amounts of red, green, or blue, or RGB, and each of these are assigned a different brightness value from 0 to 255. You can use varying amounts of red, green, and blue to create every color on the visual spectrum, so every color can be written as a list of 3 numbers between 0 and 255. For example, the baby pink of your grandma's sweater would have a value of 255 for red, 210 for green, and 210 for blue, which can be written as 255, 210, 210. And now, using what we already know, it's quite simple to then convert this into binary, which gives us this. But that's just one pixel. Each image is scanned from left to right, top to bottom, one pixel at a time. You can see our previous episodes on the TV for more on how this convention was established all the way back in 1843 by Alexander Bain. And these pixels are then converted into a stream of binary. So as a simple example, this image here, converted to binary, would look like this. In the case of HD video, that's 1920 pixels from left to right, repeated 1080 times top to bottom. And that scan happens 25 times per second. That's a lot of binary code. Now you might be thinking, how is that even possible to process that much data that fast? Well, if you remember that some of the faster chips today contain 114 billion transistors, each capable of billions of signals per second, well, you start to get the picture of how that much data can actually feasibly be sent at a near instant speed. And you also start to understand why downloading a pirated movie in the early 2000s on dial-up internet took so long, which is where we will finally be arriving after one more episode. First, we need to talk about how computers store all this data so it can be accessed. We have all this information converted into binary data now, but we need to be able to store it somewhere where we can access it easily. Which, once that's achieved, then leads to the next question of how can I give someone else access to the data on my computer if they need it? And how can I access theirs? Which finally leads us to the internet, the massive global network of computers that has allowed us such mass sharing of data that we are communicating at a speed and a scale that was unimaginable for much of human history.